Welcome to this tutorial on pseudo-Boolean solving and optimization, which is part of the bootcamp for the Satisfiability Theory, Practice and Beyond program at the Simons Institute for the Theory of Computing. So we have reached part 3 of this pre-recorded tutorial. In part 1, we learned what pseudo-Boolean constraints and pseudo-Boolean formulas are. Pseudo-Boolean formulas are collections of 0-1 integer linear inequalities. In pseudo-Boolean solving, you want to determine whether such a collection of inequalities is satisfiable, is feasible or not. We saw that we could use the ideas of conflict-driven search in CDCL solvers to solve this problem, either by taking the pseudo-Boolean formulas and rewriting them to conjunctive normal form so that we can feed them to a CDCL solver directly. Or in the other direction, we can take the conflict-driven paradigm and try to lift it from CDCL to native pseudo-Boolean reasoning, where we do propagation and conflict analysis, not on disjunctive clauses, but on general 0-1 integer linear inequalities. And if you survived till the end of part 2, which was a fairly long video chunk, then you saw that there are different ways of doing this. There are lots of degrees of freedom, lots of questions that have not been fully explored compared to CDCL. So I'd say there are lots of good open research problems there. And this is even more so when now here in part 3, we consider the setting where, in addition to the pseudo-Boolean formula, you also have a linear objective function that you want to minimize. So this is what we want to talk about now. And this topic is connected to max-sat solving, and many of the ideas for pseudo-Boolean optimization come from max-sat solving. And have been most fully developed there. So we'll talk about max-sat solving, and then we'll talk about the ideas for how to solve max-sat problems and general pseudo-Boolean optimization problems using linear search or core-guided search or implicit hitting set approaches or combinations of them. So as I already said, pseudo-Boolean optimization and max-sat solving are closely related. In order to make this precise, let us first define what max-sat is. Let's define the fully general weighted partial max-sat problem. So this is where we have a CNF formula as input, but the clauses come in two types. We have soft clauses, C1 up to CM, each clause equipped with a weight, WI, which is some positive real numbers. I think for today, it's better to think of them as positive integer numbers. And then we have a bunch of hard clauses, Cm+1 up to C capital M. And our goal is to find an assignment row that has to satisfy all the hard clauses. And then we want to maximize the amount of soft clauses that we satisfy. So we sum up the weights of all the satisfied soft clauses. And this is our objective. Except that from now on, and for the rest of this talk, we'll think about this as a minimization problem instead. Remember that we want to think of our pseudo-Boolean optimization problems as minimization problems. But here it's fairly natural. We can minimize the penalty of the soft clauses that we fail to satisfy, that we falsify. And we can write a C, a sub W for a soft clause C with weight W, and we can write a hard clause, just a C sub infinity. And it's natural to think of a hard clause as a clause with infinite weight, because then obviously if we want to minimize the penalty, then we cannot afford to falsify a single such clause, because then our objective value is infinity. So here is an example max-sat instance. We have a unit clause not X with weight 5, a clause Y or not Z with weight 4, a clause not Y or Z with weight 3, and then two hard clauses X or Y or Z, X or not Y or not Z. And it is easy and natural to translate this to a pseudo-Boolean optimization problem in the following way. So we just take all of these clauses, and we can write them as in the pseudo-Boolean form by just summing up the literals and saying that there should be greater or equal 0. But for the soft clauses, for every soft clause, we add an individual new variable. So B1 for clause 1, B2 for clause 2, and B3 for clause 3, and we add it to the clause. And now it is a common assumption in MaxSat solving that the hard part of the formula consisting of the hard clauses is satisfiable, because otherwise we have an unsat instance and there's nothing to optimize. So given that the hard clauses are satisfiable, once I've added these new variables B, clearly this is a satisfiable instance, because all of these soft clauses, I can just set the B variables to true and then they're satisfied. But now what I want to minimize is the number of such B variables that I actually use. So it's not hard to see. So I have, and I minimize by multiplying each variable BI by the weight of clause CI. And it's not hard to see that this is essentially now the same problem. So this is the so-called blocking variable transformation, where the BIs are the blocking variables. And we can see here that an optimal solution sets x to 0 and z to 0, y to 1. That violates only the cheapest soft clause, so it incurs a penalty of 3. In the other direction, we can also take a general pseudo-Boolean optimization problem and translate it into a MaxSat instance, except that it might contain pseudo-Boolean constraints instead of disjunctive clauses. So in the literature, such MaxSat instances in quotes are known as weighted Boolean optimization problems. So here is a pseudo-Boolean optimization instance. We want to minimize some wi li, where the li are literals, subject to constraints C1 up to Cn. To translate this into MaxSat, we just take all the literals in the objective function, we negate them, and we make them into soft unit clauses with weight equal to the coefficient. And then all the original constraints in the pseudo-Boolean instance, they turn into hard constraints with infinite weight. So it's clear that a pseudo-Boolean instance in such a way is just a MaxSat instance, or more generally a weighted Boolean optimization instance. And so you could, in principle, take a pseudo-Boolean optimization instance, translate it in this way. If these are general pseudo-Boolean constraints, you could translate these pseudo-Boolean constraints into CNF, as we discussed in part 2, and then you could run your favorite MaxSat solver, and then it would work as a general pseudo-Boolean optimization solver. So the MaxSat problem comes in 4 flavors. If we have only soft clauses, then it's the original traditional MaxSat problem. If we have both hard and soft clauses, then it's known as partial MaxSat, and then you can have weighted or unweighted versions of these problems, where in the unweighted version, all the soft clauses have the same weight, which then, without loss of generality, we can consider to be 1. So this gives us 4 different flavors of MaxSat, but the distinction is not so important these days, apparently, because most of the best solvers, they deal without loss of generality with the most general problem. So we, in what follows, we'll just talk about weighted partial MaxSat. And the main approaches for solving weighted partial MaxSat and pseudo-Boolean optimization that are used in current state-of-the-art solvers are linear search, known as linear search sat unsat, or model improving search. We'll start talking about this. And then we will talk about another approach that is called core-guided search. And then finally, I'll mention something briefly about implicit hitting set approaches for solving MaxSat and pseudo-Boolean optimization. And throughout, our perspective will be, we'll think about the problem of minimizing an objective function summing over I, wi, li, subject to a collection of pseudo-Boolean constraints C1 up to Cm, which could be disjunctive clauses or maybe general pseudo-Boolean constraints. So what this means is, in some sense, we, if it's a max-sat problem, then we have already done this blocking variable transformation. Good. So what is linear search? Well, it's perhaps the most natural approach you could think of. We just run the solver. So we start out by saying that we don't have a solution. So the best solution is nothingness. And then we run our solver. In max-sat, it's a sat solver. If it's a pseudo-Boolean optimization problem, then maybe it's a pseudo-Boolean solver. If the solver returns unsatisfiable, then we output whatever we have as the best solution and terminate. Otherwise, we found a solution, row, an assignment to the variables. Let's update row best to be this solution. And then we can evaluate the objective function. And under row, this gives value wi times row I, summing over I from 1 to n. And now we add a constraint asking for an objective function value that is 1 smaller than this. So we add this constraint and then we run the solver again. So now, next time, either it will have to return a better solution, in which case we update, or if it turns out that we already found the best solution, then the solver will return unsatisfiable, and then we return the best solution. Here is a small toy example. Suppose we have a pseudo-Boolean formula f, which we'll just consider to be a black box. We don't know what it is, but the objective function is minimizing, say, x1 plus 2x2 plus 3x3 plus 4x4 plus 5x5 plus 6x6. Okay, good. We run the solver, and it returns the assignment that x1 up to x3 and x6 are 0, but x4 and x5 are 1. So now we evaluate the objective. So we get a contribution only from x4 and x5, and the others contribute 0. So the objective function value here is 9. Now we want a better solution than this, so we add the constraint that the objective function should be less than equal 8. Note that this is not a normalized constraint because it is not a greater than or equal constraint, but we agreed already in part 1 of this tutorial that we know how to convert this into normalized form, and here it is convenient to use this syntactic sugar to think of this as a less than or equal constraint. Good. We run the solver again on the original formula f plus this new constraint in red. And now suppose it sets x1, x3, x5, and x6 to 0, but x2 and x4 to 1. Then the objective value is 6. So we add a constraint saying that we want the objective function to be less equal 5. And we run the solver again. And now suppose the solver returns unsatisfiable. So this means that it wasn't possible to find a solution to the pseudo-Boolean formula f that yielded objective function value 5 or smaller, but we do have a solution with value 6 that has to be the optimal solution, so we can return 6 as the optimum. That's linear search. And now, especially if you know your algorithms, you're a theoretician, you ask, well, why are we doing linear search? Why are we not doing binary search here? And the answer is that apparently linear search is better. So there are at least 2 possible explanations for this. One is that, well, in theory, why is linear search bad? Linear search is bad because it could be that you just improve the objective value by an additive 1. So you have to rerun it and rerun it over and over again, and you get only very small gains in objective function value. In practice, apparently, this does not happen so much. Even when you do linear search, the objective function value tends to jump quite a bit. Another, perhaps more important reason is that when you're doing binary search and you're using a SAT or pseudo-Boolean solver as an oracle, not all calls to this oracle have equal cost. Because some of the calls will be for satisfiable instances where you just want to find a solution that is better than the solution you already have, but there is such a solution. And then some calls will be unsat calls, which is where the solver determines that you're asking for an objective function value that is too good to be true. And it tends to be the case that these unsat calls are more expensive than the sat calls. So if you do a binary search, then it might be that every, a lot of your calls might be unsat calls, and so they might be quite expensive compared to going with linear search and getting all calls sat calls until only a final expensive unsat call. Another nice property of linear search is that you get a solution fairly quickly. Even if it's not the optimal solution, even after the first time your solver returns, you have some solution. And then you work on improve it, but you have something. And this is important for what is sometimes referred to as anytime solving, which is a setup where you don't only solve for optimality, but time is also limited. So you're interested at every point in time to have the best possible solution available with that limited amount of computation. And it can be argued that in applied settings, this is a very important setting. Quite often, you might not have patience to wait for hours and hours to squeeze the final bit of optimality out of your solution. If you can get an almost optimal solution quickly, then you're very happy with that. But the problem, of course, with linear search is you don't know how good your solution is because you have no handle on what the lower bound might be. So that's what I wanted to say about linear search SAT-unsat, or the LSU algorithm. Now we switch gears and talk about so-called core-guided search. We still want to minimize the sum wi, summing from for I goes from 1 to n, subject to some collection of pseudo-Boolean constraints. And when I want to describe core-guided search, it's convenient to first think of this as a max-sat instance where Li are these blocking variables that we have introduced. So the meaning now of a literal Li is that it represents a soft clause. And this is the reason why this is important, is that this explains some of the terminology that is used, although we will generalize it shortly. So now the idea is the following. We want to be optimistic. So we say that, in fact, the best possible value is 0. We can minimize everything. We can set all the literals to 0. And we run the SAT solver, since we're doing max-sat, we run the SAT solver with these assumptions, assuming Li to 0 for all literals in the objective function. And usually SAT solvers have a special API where you can tell it to, in addition to the decisions that it's going to make on its own, you give it a list of pre-made decisions to be applied at the beginning. And then what the SAT solver will do, it will apply all these decisions, and then it will either find a solution that is consistent with these pre-made decisions, these assumptions, or it will return an explanation, a clause, showing why these assumptions are not consistent. Okay, why you can't make all of these assumptions. So we run the solver, and now it should be clear that if it returns satisfiable, then we have indeed found the optimal solution, because we were wildly optimistic, but this bet paid off. We found a fantastic solution, so we're happy. Clearly, 0 is the best we could hope for, since all the weights wi are non-negative. Otherwise, what the solver does, it's returning some clause that explains why the assumptions are inconsistent. So say the learned clause is Li or L1 or L2 up to Lk, which says that no, you cannot assume L1, L2 up to LK all false. At least one of these literals has to be true. And what this means in a max-sat setting is, no, you have to violate at least one of these soft clauses. You cannot find a satisfying assignment that satisfies all the hard constraints plus all of these soft clauses. This is not possible. And in max-sat terminology, that means that these soft clauses, C1 up to CK, form a core. Okay, this is what is known as a core, and this is why it's called core-guided search. So now we know that in this core, at least one clause has to be false, at least one blocking variable Li has to be used, but possibly more. We don't know, maybe all of them. So we have to violate at least one of these clauses, maybe all K of them. We don't know how many. So conceptually, we now introduce new variables, Zj, where we think of Zj as meaning that J out of these literals L1 up to LK are true, that J of the soft clauses have to be falsified. And then we can update our objective function by using the equality that we know that, well, the sum of the Li is at least 1 plus summing for j goes from 2 to k Zj for these new variables j. And now we can use this equality, we can plug it into the objective function, and we will multiply it by the smallest coefficient of any Li. And then we'll get a cancellation. We'll cancel that Li and we'll substitute the Zj's instead, and we'll get out a constant term here that will give us an update that says that, well, this is a lower bound on what you could hope to achieve. You can't get all the way down to 0. You have to have an additive term at least such and such. And this allows us to update the best value. So this is going very fast and I'm not explaining it very well, but we'll do an example shortly, a more general pseudo-Boolean optimization example. So bear with me for a minute. The important thing is that in some way we can introduce these new variables which have the intended meaning that sum of L1 up to LK is equal to 1 plus sum of Z2 up to ZK. And then we can use this equality to rewrite the objective, get an updated lower bound estimate. And then we just keep this, we store this additive lower bound somewhere. And then we assume that the rest of the objective function can again be 0, and then we repeat from the start. And we just run this over and over again, deriving new cores. Okay. Until we get the answer satisfiable back. And when that happens, the current estimate best value is indeed an optimal solution. Okay, and this original idea in MaxSat comes from a paper by Fu and Malik and has been developed in a number of different directions. So see this survey in the references. Again, the references are at the end of the slides, and you find the PDF with the slides on the Simons Institute webpage. I will also show the slides in the fourth and final video in this pre-recorded tutorial. They are at the end of the PDF file with my slides. And you can view core-guided search. It's again a linear search, but it's not sat unsat. It's coming from the unsat side and moving towards the sat side. And this idea of introducing these new variables to keep track of how much of the core is violated has been used in answer set programming and in max-sat solving. So now we want to translate all of this to a general pseudo-Boolean setting. And now the nice thing here first is that we don't need to think of the LIs as blocking variables or markers for soft clauses or something. We just have a general pseudo-Boolean problem. This is an objective function, whatever. The LIs are just literals. There are no soft clauses, no nothing around. We'll still talk about cores, but there are no, like, there will be no soft clauses or anything. Okay. Another thing is that this rewriting that we did, I'm going back again, will actually be very convenient here, because in a maxsat setting, if you want to actually encode this, you'd have to rewrite to CNFs in some way. But in a pseudo-Boolean setting, this will just be, an equality is just two pseudo-Boolean constraints that you can just write down, and then you're done. I'm sweeping a little bit of details under the rug, but essentially this is very cheap in a pseudo-Boolean setting, because the constraints that you need are already available as native constraints for the solver. So you can do core-guided pseudo-Boolean search, which just assumes that the objective function you have can reach its best imaginable value, and then you derive a contradiction if this is not possible, and essentially run the algorithm we have on the previous slide. So let me, rather than giving you pseudocode because it gets a bit messy, let me just try to explain the idea by a concrete toy example. In fact, the same example as before. We have this pseudo-Boolean formula f. I'm not telling you what it is, but we have the objective x1 plus 2x2 plus all the way up to 5x5 plus 6x6. And now we're going to solve this pseudo-Boolean optimization problem with core-guided search. So the first assumption is that, well, the best possible value is 0, right? So we set all the variables xi to 0 and run the solver. And now also a pseudo-Boolean solver can be developed to have this assumption mode, where it will do one of two things. It will apply all the assumptions, then it will solve the residual pseudo-Boolean formula under these assumptions, and it will either return a solution, in which case we're happy, or it will return a pseudo-Boolean constraint that explains why these assumptions are inconsistent. How do you do this? Well, in technical terms, it's not so hard. You just run your solver on with the standard conflict analysis, and then once you know you can extract a core when you get a conflict already at the level that is at the decision level of the last assumption or earlier. Because if you get a conflict in the solver only after applying assumptions, then you know that the conflict is explained only by your assumptions. Now, if you run your standard learning algorithm, you might pick up other literals also, but you can switch to the so-called decision learning scheme, which resolves away all reasons all the way up to the beginning of the trail, and then you will get a constraint that only involves the assumption variables. So suppose that we get such a constraint back, and it turns out that the constraint is 3x2 plus 2x3 plus x4 plus x5 greater or equal 4, say. Okay. So it turns out that this constraint, if I want to do pattern matching on the maxsat core guided algorithm we had before, it's not so easy to deal with this general pseudo-Boolean constraint. So as we discussed in part 2 of the tutorial, you can take any pseudo-Boolean constraint and you can round it to a cardinality constraint. So I can look at this constraint and I can say, what's the best cardinality constraint I can get from it? Well, if the only way that this constraint is true is that at least 2 of these variables have to be true. So I'll round this constraint to a constraint saying x2 plus x3 plus x4 plus x5 greater or equal 2. This is certainly implied by the pseudo-Boolean core constraint, and I'll call this cardinality constraint the cardinality core constraint. So now we want to do, now we know that the sum of these variables is at least 2. The pseudo-Boolean solver told us this. And the sum can be at most 4, clearly. But we don't know where it is between 2 and 4, and we want to store this information. And the way we're going to do this, we're going to introduce 2 new fresh variables, y3 and y4, and write down pseudo-Boolean constraints. Again, I'm using syntactic sugar here, but it should not be hard to see that these are actually pseudo-Boolean constraints. First, I'll write down constraints enforcing that x1, x2 plus x3 plus x4 plus x5 is equal to 2 plus y3 plus y4. And the reason why this is sound, I mean, this would not be a sound constraint in general, but we know that the sum of these variables is at least 2. The solver told us this, so that's why we can write down this constraint. And then I'll also enforce that y3 is greater or equal to y4. And now if you think about it for a second, you realize that these constraints 4a and 4b actually enforce what I wanted it to enforce, namely that yj is true precisely if sum of x2 up to x5 is greater or equal to j. So now what I want to do next is I want to update the objective function using this. So let's go back to the previous slide. And here is the objective function in 1. And in 4a, I have an equality. So I can multiply this equality by 2. And then I can substitute y2. Well, because I look at what the coefficients of x2, x3, x4, and x5 are, and the smallest coefficient is 2. Okay, so I multiply the equality 4a by 2, and then I can substitute 2x2 plus 2x3 plus 2x4 plus 2x5. I can substitute that by 2 times 2, that's 4, plus 2y3 plus 2y4, because this is an equality. Let's do that. So here is the new objective function, which is equivalent to the old objective function, because of these constraints 4a and 4b that I've introduced, the original objective function 1 is equivalent to this modified objective function 5. And note that in this new objective function 5, I have picked up a constant term 4, which indeed tells me what I learned from this cardinality core, namely that it is not possible to achieve 0 for this objective function. So far, I know that the best possible value is 4. Maybe 4 isn't achievable either, but you can't do better than 4. Good. So now I run the solver again, assuming all literals to being 0 in the updated objective function. So I assume x1, x3, x4, x5, and x6 to 0. Note that x2 canceled and is no longer around. In addition, I assume y3 and y4 to 0. Let's run the solver again and see what happens. So it turns out that the solver now returns not a general pseudo-Boolean constraint, it just returns a clause. And that will happen a fair amount of the time. You'll just get a clause back in here. Suppose we get the clause x4 plus x5 plus x6 plus y3. At least one of these literals is true. And what do we now? Again, we know that at least one of these literal is true. We know that 4 of them could be true. We don't know whether 1 or 2 or 3 or 4 of them will be true. We want to store this information, so we'll introduce new variables again. And so since we already have a clause, there's no need to rewrite a general pseudo-Boolean constraint to a cardinality constraint, because this is already a cardinality constraint. So we introduce new variables z2, z3, and z4, and we can write down this equality then, that x4 plus x5 plus x6 plus y3 is equal to 1 plus z2 plus z3 plus z4. And this is sound because we have this lower bound in 6. So that's why we can plug in this 1. And then we add in addition constraints that z2 is greater or equal to z3, that is greater or equal to z4. And these constraints 7a to 7c will enforce the meaning of zj as the sum of x4, x5, x6, and y3 is greater or equal to j. And now what we're going to do again is we're going to look at the coefficients. We want to use this equality 7a and update the objective function. And now x4, x5, x6. x4 appears with coefficient 2, x5 with coefficient 3, x6 with coefficient 6, y3 with coefficient 2. That means that we can multiply this whole equality with a 2 and then substitute 2 times the left-hand side here. We can replace that by 2 times the right-hand side. So 2z2 plus 2z3 plus 2z4 plus a constant term 2 that will provide a further update of the lower bound estimate in our objective function. So let's see what we get. We get this. So now we have an equivalent objective function again, x1 plus x3 plus x5 plus 4x6 plus 2y4. Note that y3 cancelled here. And also x4 cancelled. And instead we have 2z2 plus 2z3 plus 2z4 plus the 4 we had before is now updated to 6. So now we see that we don't know what the optimal value is, but it's at least 6. So the best value estimate, we updated to 6. And now for the third time, we run the solver again, and we assume all of these literals in the objective function to false. Okay, and now you remember in our linear search toy example, there was in fact a solution with value 6. So that should be the case here as well. And indeed, our pseudo-Boolean solver finds it. It reports that x1 equals x3 equals x5 equals x6 equals y4, z2, z3, z4. All of them can be assumed to false, and there is such a solution. Fantastic. So then we know from this that we can read off the original solution. We can go back, for instance, to if the solver doesn't already tell us, then we can figure out ourselves from 4a, which was this constraint where we introduced y3 and y4. So when we apply this partial assignment, 4a simplifies to x2 plus x4 is equal to 2 plus y3, and the only way this can hold is that y3 is 0 and x2 and x4 are 1. So that means that we can read off the original solution in the x variables. And indeed, we get, so x2 and x4 are 1 and all the others are 0. And looking at the original objective function, we had x2 and x4 1 and all the others 0. So indeed, we do get objective value 6. But this we already knew because note that due to our rewriting, this objective function in 8 is equivalent to the original one because we only transformed it using equalities. Okay, so this is an explanation by example of how core guided search works. And what are some interesting properties of this algorithm if we run this pure core guided search that I discussed here? Well, it turns out that we can, if we're lucky, we can quickly get a lower bound on the solution. And this is nice because this helps us if we have a good lower bound, that this already allows us to ignore large parts of the search space where the objective function value would just be too good to be true. However, the way the algorithm works here, we know nothing about the solution until we finally hit on the optimal solution. So we know nothing until we have the optimal one, and depending on what you want, this might not be what you're after. Also, although we do have a lower bound, we have no idea how far away this lower bound is from a feasible solution because we're only increasing the lower bound. So this is complementary to linear search, which was good at finding a solution, an upper bound, but there we had no clue about the lower bound. So it's a very natural question to ask, well, maybe can we somehow combine core guided search and linear search to get matching upper and lower bounds? Here are some ideas that have been explored for how to do this. The first one is stratification or weight stratification. You look at the objective function, and maybe some literals have very heavy coefficients and other ones have not so heavy coefficients. So some coefficients are large, others are small. And if there's a large difference in coefficient weights, then do the assumption only assuming literals with large weight coefficients to false, but don't assume anything about the others. So this can lead to one of two things. So if it turns out that already this very limited assumption on these large weight literals, if already that is inconsistent, then since you made fewer assumptions, you get a smaller, more compact core, a stronger core. Okay. Another thing that can happen is, of course, that, well, in fact, assuming these high weight literals to false was consistent. So you sort of accidentally find the solution, but that's great, because then we actually have a decent solution, and we can continue our core guided search, but we have at least some kind of solution. And note that this was what the linear search gave us before, but that we were missing in the pure core guided search approach. Another idea to amortize the work done, as it were, during the core guided search is if we assume all the LIs from, say, 1 to n to false, and then we learn a core constraint that only involves L1 up to LK, then we can say, okay, now we know that at least one of these literals has to be true. What about the other ones? Maybe there are other connections in between the other literals that we have not explored. So let's just remove L1 up to LK from the list of assumptions. Let's assume the other literals to false and run the solver again with these remaining assumptions. And if we now get a new core, then obviously this core will be disjoint from the core we previously had over L1 up to LK. So in this way, we can collect a number of disjoint cores, and then we can update the objective function and get a lower bound update independently with all of these independent cores, disjoint cores, individually contributing to the update of the objective function, lower bound. Another idea is called core boosting. So here what we do is remember that I said that the nice thing with core guided search is that it can quickly give us a fairly decent lower bound on the objective function that cuts off large part of the search space. So with core boosting, you just do that. You run core guided search for a while to hopefully get this good lower bound estimate. And then you switch to linear search and stay with linear search and try to find an optimal solution, hoping that the lower bound during the core boosted, the lower bound that you found from core boosting during the core guided search helps you to do this. A more refined idea is to interleave core guided and linear search so that you would start doing maybe core guided, then switch to linear search for a while, then switch back to core guided search, then again do linear search. Now, this apparently is not done much in MaxSat solvers. And my understanding is that the reason for this is, in fact, that all of these steps that I described with updates of the objective function and rewriting, note that we were operating with pseudo-Boolean constraints. And this doesn't come for free because in a CNF setting, there's a lot of re-encoding involved. And this is fairly expensive and takes time. So doing this switching back and forth between core guided and linear search is fairly costly if you're operating on CNFs. But if you're operating natively on pseudo-Boolean constraints, then in fact, this is not expensive at all. Then you can do full interleaving search fairly cheaply. So this is another advantage of a native pseudo-Boolean solving. One thing that we cannot do in a pseudo-Boolean solver, at least not yet, but you can do in a CDCL solver. Just as in CDCL conflict analysis, you do clause minimization during learning. Here you can also do core minimization, because the core that you learned is just a learned clause as any other clause. So you can try to minimize the core in different ways. For a pseudo-Boolean solver, it's not so clear how to do this, but maybe something can be done, although to the best of my knowledge, I don't know of anything that has been implemented in this regard. And I should note that this, in general, this idea of minimizing the constraints that you learn during conflict analysis is an interesting problem for pseudo-Boolean conflict analysis in general. One implementation detail that turns out to be important is that when we did this rewriting, let's go back and see, time and again, we had these equalities where we introduce here, for instance, we introduce new variables Z2, Z3, and Z4, and did this rewriting. Now, in a real-world instance, you'll find many cores. And if these cores are large and are clausal, then you'll get tons of new variables. And in fact, performance will take a hit after a while. And then it turns out that you could sort of be lazy here and not introduce Z3 and Z4. You could just introduce Z2. You'll have to use a different encoding, but you could just introduce Z2 to mean as an indicator that, in fact, more than one of these literals are true. And then introduce Z3 and Z4 later only when needed. So this is something that is called lazy variables, lazy introduction of variables. Here we are. And this can be pretty important, but I didn't describe it here because conceptually it's not really a difference. It's more of an implementation detail. So why is core-guided search good? I don't know, but from a theoretical point of view, one very interesting observation is that these new variables that we're introducing, they are extension variables. And we know from proof complexity that even just the resolution proof system, if you add extension variables, then it becomes extremely powerful. It becomes as powerful as extended Frege, which is one of the strongest proof systems that we know. And also, if we take a pseudo-Boolean solver and add extension variables to it, then it becomes some version of cutting planes with extension variables, which is also equally strong. It takes us all the way to extended Frege. Now, the problem with why these proof systems with extension variables are not used is that although they're strong in theory, it's very hard to see in practice what would be good heuristics to introduce extension variables and make use of them. But what is interesting here is that core-guided search provides such a heuristic for which extension variables you should introduce and why. So one interesting question from a theoretical point of view would be to formalize what core-guided search can do. And given that extension variables are introduced in this way, it would also be interesting to characterize limits of the powers of this method to see if we can pin down, maybe there are some things that it cannot do. So a better theoretical understanding here would be quite interesting. This, I just want to report briefly, this is actually something that we try to do. If we try to evaluate, we implemented core-guided search in a pseudo-Boolean solver in the solver rounding set that was mentioned in part 2 of this tutorial. And we have explored different flavors of this, combining core-guided search and linear search. Let me present on a bunch of different benchmark families a number of instances that are solved to optimality with different approaches, the best solver configuration in red, then blue, then green. And don't look at the last line of this table for now, try to just don't look at it. We'll discuss the other lines first. So our favorite setting was the solver that dynamically interleaves core-guided search and linear search and switches back and forth. This was a competitive approach in general. So we ran it on the latest Pseudo-Boolean competition from 2016, the 16,000 competition benchmarks. There's also a MIP-lib that is used for evaluations in the mixed integer linear programming community. We took some 0-1 integer linear programs from there, optimization problems, ran on those. There's a collection of challenging knapsack instances by Pissinger. And then for other reasons, somewhat independently, somewhat depending on this, we have a collection of tricky benchmarks originating in proof complexity. So these are combinatorial formulas, which are sometimes referred to over on the applied side as crafted formulas. So we have a particularly tricky set of crafted formulas that challenge the solvers in different kinds of theoretical ways, measuring their strength of inference. And we can see that the hybrid solver overall performed very well on these benchmarks compared to the rounding set version that we had before that only does linear search. You see that it's a fairly significant jump in performance on the Pseudo-Boolean competition benchmarks, and even more so on the crafted benchmarks. Interestingly, for knapsack, linear search is still better. And for the MIP instances are in general just hard for Pseudo-Boolean solvers, but at least it seems that hybrid helps a bit. Another very competitive approach, as we can see, is the core-guided approach where you don't interleave, but 10% of the time we run core-guided search and then we switch, and until the timeout we just run linear search. That's also very good. We try to investigate how much the different aspects of the implementation contribute. So one interesting thing with Pseudo-Boolean solvers is that the cores are not necessarily clausal. They can be general cardinality constraints. So we try to switch this on and off. And we can see that the fact that you can get non-clausal cores actually seems to contribute fairly significantly. Not always, but usually there's a boost in performance when you can have also non-clausal cores. Lazy variables are very important if you want to solve knapsack. And this is because for the knapsack constraints, you have lots of different weights. And it turns out that you can get very many new variables if you're not lazy. So that's why you have this huge jump here. And then we tried this interleaving solver with both lazy variables switched off and the non-clausal cores switched off. And as expected, it's mostly worse, not always, but for most of the instances. So here we can see we're evaluating against two other Pseudo-Boolean solvers, Sat4j, that I've been mentioning before, and NAPS, which is a CDCL-based solver. They are very competitive or even better than this linear search rounding set on the Pseudo-Boolean competition benchmarks. But we see that once we throw in this core-guided component, rounding set gets much, much better, except for knapsack, where it seems that the tricky part is to find good solutions. And here somehow rounding set is not doing well. Now, finally, the sad part is that Skip is an academic MIP solver. It's not the best MIP solver, but it's the best non-closed source solver. And unfortunately, it beats the crap out of all Pseudo-Boolean solvers. So there's room for improvement here, and this is why you should also stick around for part 4 of this tutorial, where we'll talk a little bit about what solvers like skip do. But I should say that there are skip and the hybrid rounding sat solver have somewhat complementary strengths. Also, it should be noted that skip uses pre-processing, and none of the pseudo-Boolean solvers do that. So maybe we should do that. I think there's room for improvement here by taking the best techniques from skip and the best techniques from pseudo-Boolean solvers and try to combine them, and maybe also use other techniques like the implicit hitting set approach that we'll discuss shortly. Oh yeah, here are also a plot from a cumulative plot for the Pseudo-Boolean competition 2016 benchmarks. So here we're plotting number of solved instances as a function of time with a logarithmic scale. And here we also tried to introduce these ideas with weight stratification and trying to find independent cores. Interestingly, for the instances in the Pseudo-Boolean competition benchmark set, it turns out that this doesn't pay off. So weight stratification, there's not such a big difference. Sometimes it pays off, sometimes it doesn't. It's actually hit or miss whether you want to use stratification or not. But independent cores doesn't seem to be good. So one possible explanation for this could be maybe selection bias. That because there is a selection bias in these competition benchmark sets, or maybe we somehow didn't implement independent cores as it's done in the best state-of-the-art max-sat solvers, or maybe it's something else entirely. We don't know. That's what I wanted to say about core-guided pseudo-Boolean optimizers. Now the third and final approach I want to talk about, I'll do it more briefly, is the so-called implicit hitting set algorithm. Again, recall that we have this generic setting. We want to minimize sum for I goes from 1 to n, wi li for literals li, subject to some collection of pseudo-Boolean constraints. And since we're coming from max-sat, again, let's think of these as clausal constraints. Let's think of these li as blocking literals. So they're names of clauses, as it were. So as in core-guided search, we'll solve with assumptions and we'll collect cores, but we collect a whole set of them and keep this set. So cores will be clauses, and the meaning of this clause, so these literals L are like names of literals, and the first core says that, well, you have to falsify at least one of these clauses, and then the second core says you have to falsify at least one of these clauses, and the core number S says that you have to falsify at least one of the clauses tagged by these literals. Okay, so in all of these sets, you have to falsify at least one clause. Now, one way of trying to do this as economically as possible is, well, pick as few literals as possible so that you hit all of these clauses. So pick a hitting set. So this is what we're going to do. So the way the implicit hitting set approach is, we start with a set of cores that is empty at the outset, and we'll grow with the cores that we collect. And in every iteration, we compute a minimum hitting set for k. That is a set of literals such that every clause in the core set has some literal in H. So in terms of sets, H is a hitting set. What this means for truth value assignments is that if we set all the literals in H to true, then we're satisfying all of these clauses. And we know that we have to, so satisfying all of these clauses means that we're violating some original clause in these cores, and this we know we have to do. And we're trying to do it. The fact that we're using a minimum weight hitting set means that we're trying to falsify soft clauses in the cheapest way possible. And once we figured out this minimum hitting set H, we run the solver with this assumption. So the literals in the hitting set, we'll assume them to true. We take the penalty. Everything else, we try to assume to false. Now, if the solver run with this assumption finds a solution, it must be an optimal solution, because we know that we have to pick one literal from all of these clauses, and the minimum hitting set is doing this in the most economical way possible. So therefore, if the solver finds a solution with the minimum weight hitting set, then this solution is optimal and we can return this value. Otherwise, if the solver does not find a solution, it returns a new core, which we add to K, and then we start over again, compute a new hitting set, and do another round of this iteration. And one observation is that when are we using minimality? We're only using minimality here, that when the solver finds a solution, it's optimal since the hitting set is optimal. So this means that in early iterations, we can just compute decent hitting sets, not necessarily optimal ones. We only need to check optimality at the very end. So a natural question is, yeah, but where do we find the hitting sets? But it's not so hard to see that this minimum weight hitting set is in fact another pseudo-Boolean optimization problem. We even discussed this in the preliminaries part of the tutorial. So you could actually imagining running your solver on this subproblem and taking that solution. Or I think what is done in practice is usually you run a MIP solver and you take the solution from the MIP solver. So how good? So this is another approach than core guided. So how do they compare? So with the caveat that I have not done research on this, but I've talked to colleagues who know this better than I do, and they're fairly consistent in saying that it's not the case that either approach dominates the other. So it seems that implicit hitting set and core guided have complementary strengths. For max-hat problems where you have many soft clauses with the same weights that are somehow interchangeable, and the important thing isn't exactly which soft clauses you violate, it's more like about the count of how many soft clauses you need to violate. Core guided seems better because it will allow you to abstract away and somehow give you this count. It doesn't necessarily care about which clauses, it will just know how many clauses you're violating. However, for max-hat problems where you have many distinct weights, it seems that the implicit hitting set approach is often better. This is all based on intuition, though. So a very nice question for the theoreticians listening to this would be to study the proof complexity of core-guided search and implicit hitting set and try to provide precise characterizations, compare the two approaches. Maybe you can prove some simulation results or separation results. There is some work in this direction, but there's definitely room for more. Other open questions, since implicit hitting set and core guided are complementary, why not try to combine them? So it turns out that somebody already thought about this. There is some recent work on this, but again, my impression is that it's not the final word. There should be more things that can be done here. Another idea is to think about, well, can you do implicit hitting set for general pseudo-Boolean optimization? So now remember that we don't have cores and soft clauses here. We just have an objective function and literals. So the so-called cores will just be learned pseudo-Boolean constraints over literals in the objective function. So then what is a hitting set? Well, a hitting set will be a partial assignment that is guaranteed to satisfy all of these constraints. Note that if these constraints are clauses, then the hitting set is really just a hitting set, because you know for every constraint that you only need to satisfy one literal in C, and then the clause is satisfied. In general, if the CIs are pseudo-Boolean constraints, then you might need to set several literals to be sure to satisfy this constraint, and you'll get some kind of generalized hitting set that does this in as cheap a way as possible. To the best of my knowledge, this has not been implemented in a native pseudo-Boolean solver. I think it would be very interesting to do it. But that's a future research direction. That ends part 3 of this tutorial. So we've now talked about what pseudo-Boolean problems are, how to solve decision problems, how to solve optimization problems. But as you saw, the annoying thing is, as we developed these solvers, often, not always, but often it turned out that mixed interlinear programming solvers were also very good at solving these problems, or even better. So in the 4th and final part of this pre-recorded tutorial, we'll talk a little bit about what these mixed interlinear programming solvers are, how they work, and what we can do about the fact that they're so good. So we can try to beat them, or we can try to join them, or maybe do both. But to hear more about that, you have to tune in for the 4th and final part of this tutorial. This ends part 3.